Meeting together in the headquarters of the BBVA Foundation in Madrid to deliberate and decide, the committee has resolved to grant the BBVA Foundation Frontiers of Knowledge Award in the climate change category in its 16th edition to Dorthe Dahl-Jensen, Jean Jouzel, Valérie Masson-Delmotte, Jakob Schwander, and Thomas Stocker for contributions to the polar ice core records that establish a fundamental coupling between greenhouse gases and air temperature, characterizing climate change over the past 800,000 years. These records, from the thickest and oldest ice deposits on the planet in Antarctica and Greenland, show that changes in atmospheric concentrations of greenhouse gases, including carbon dioxide and methane, are accompanied by systematic changes in ambient air temperature across the globe. The polar ice records further reveal the natural variability of Earth's climate, thus contextualizing current greenhouse gas concentrations and associated global warming. A signature finding from the ice core record is that over the past 800,000 years, greenhouse gas concentrations, due to natural variability, have never reached the atmospheric levels seen today. These achievements required scientific, technical, and logistic breakthroughs in many areas to measure greenhouse gas concentrations and interpret water and carbon isotopes trapped in ice cores several kilometers long. This further required novel analytic frameworks using a hierarchy of models. The contributions recognized here build upon sustained international collaborative efforts by generations of researchers.
What has your research on ice cores in Greenland revealed about the relation between greenhouse gases and air temperatures that characterize climate change?
Well, one of the very amazing things about our ice core research is that the ice tells us both what the temperature is through the stable water isotopes and what the greenhouse gas concentrations are through the trapped air in the ice matrix. We see that the temperature increases first and the CO2 follows. But we also know that when the temperature increases, the temperature of the ocean warms and it releases CO2 through the atmosphere. And then we see it's a positive feedback mechanism that the increasing CO2 gets the temperature to rise more, which gets the CO2 to rise. And in that way, we get the warming we observed in the past.
And on the basis of your research, how severe could the impact of sea level rise be due to the current global warming provoked by human activity?
At the moment, we have a global mean sea level rise of 3.5 millimeters per year, where most of it is coming from the Arctic ice, both the Greenland ice sheet and the smaller ice caps in the north. It's predicted that the sea level rise will reach up to 1 meter until year 2100. But we also know that if we see some of the severe instabilities we've had in the past, we learn from the ice cores, maybe the sea level rise can be up to 1.7 meters before we reach year 2100. This is something that really will impact life many places on Earth.
Are we in time to prevent the worst scenarios of climate change? And if so, what measures do you think must be implemented to confront this global challenge?
Well, I would say we have to be in time because this is where we are, and we can do a lot to stop releasing greenhouse gases into the atmosphere. So I think that's the first, that we need to stop emitting greenhouse gases, stop using fossil fuel, and use green energy. Are we in time? Yes, we are in time. And but if we wait, the consequences will be more severe because the greenhouse gas is still warming our world, and it will do so the next 100 years, even if we don't emit more. So we will get a further warming, even though we don't emit greenhouse gases. So it is now we have to start reacting and decrease our use of fossil fuels.
How has your research contributed to establishing the link between greenhouse gases in the atmosphere and Earth's surface temperature?
So this comes from the 80s. Thanks to our colleague Claude Lorius, we had access to ice core sample from the Vostok ice core, which was drilled by Soviet colleagues in Antarctica. And this sample, for the first time, covered the full glacial interglacial cycle. And in our laboratory, thanks to mass spectrometer, we were able to analyze the isotopic composition of this ice, which give access to the temperature of the site, and indeed, which is largely at this time scale give a good understanding of atmospheric temperature at the global level. And our colleagues from Grenoble were the first team with Dominique Reynaud and his team, Jean-Marc Barnola, Jérôme Chaplas, to be able to measure the composition of the air bubbles in greenhouse gases, carbon dioxide and methane. And we saw at that time that there is during the last glacial period, there is less greenhouse effect than during warm period. It's clearly, there is a clear link between the variation of the temperature in Antarctica and at global scale probably, and the composition of the atmosphere in greenhouse gases. It's probably trop long.
Given your experience in researching and advising on climate matters, what measures should global leaders adopt in the face of the current climate crisis?
So I have the opportunity to participate to the climate convention, COP28 last time, and it's clear that the conclusion of this COP, Conference of Parties of the Climate Convention, are based on our diagnostic of scientific community through the IPCC report. And so this is nice, but there is a gap between the objectives which are taken in consideration in this global statistic and the reality. And I mean, we should be able to fill out this gap between objective and the reality, and this is we should do that with a rapid decrease of the amount of greenhouse amount of greenhouse emission in the atmosphere. It should be decreased very rapidly in order to reach carbon neutrality in 2050, and there is a lot to do to really reach this objective.
What has been your contribution to the study of ice cores as a means to understand the climates of the past and predict their evolution into the future?
I've worked on ice cores from Greenland and Antarctica, spanning up to 800,000 years, in particular to quantify past changes in polar temperature, to understand the mechanisms of polar amplification, and to test the skills of climate models also used to project future changes.
What does your research predict will happen in Antarctica by 2070 under pessimistic and optimistic climate scenarios? And what would be its impact on the rest of the world?
What really matters is that what happens in the rest of the world affects polar regions, including Antarctica, through greenhouse gases and their consequences. And what happens in polar regions affects the rest of the world, in particular through sea level rise. So we have combined insights from ice cores about the past state of the Antarctic ice sheet for different levels of global warming with climate projections in order to depict very contrasted futures. If global warming is limited by sharply reducing greenhouse gas emissions, we could avoid major changes in the Antarctic region. However, if greenhouse gas emissions are stable or continue to increase, then we expect major changes, and by 2070, the risk of irreversible consequences, in particular from the flow of the Antarctic ice sheet, committing sea level to rise by several meters over several centuries.
Are we in time to prevent the worst impact of climate change? And if so, what measures do you think must be implemented to confront this global challenge?
We still have a capacity to act, we have agency, but there is urgency to implement climate action in three main directions. The first one is to act on the cause of global warming, which means implementing all the solutions to reduce greenhouse gas emissions as fast as possible. And there are technological solutions, solutions based on nature, and of course, solutions based on sufficiency and lifestyle changes. We also have to adapt to a changing climate by anticipation, not just by reacting to what has already happened, but building on what we know of what will be future changes so as to limit the consequences. And finally, we need to support those most vulnerable who have the least capacity to act. And amongst that, I would like to insist on one enabler, which is enhancing climate literacy, including knowledge we have from ice core science.
Could you tell us about the innovative tools which you developed and how they helped to improve ice core drilling?
During the last 10 to 15 years, we developed at the University of Bern a fast access drill that is a very lightweight system. It drills a hole of only 20 millimeters diameter, and ultimately we should be able to reach a bottom of an ice sheet 3 kilometers thick within 2 or 3 weeks. In this hole we can lower a logger that measures temperature and dust in the ice, among other things. And with this information we should be able to determine the age of the ice at this site. And doing this before a deep drilling is started, we could potentially avoid a bad drilling site and then by this save money and time.
What have these technological innovations contributed to our understanding of climate change in the past and the present?
The Fernair sampling, the Fernair device, helped a lot to improve timescales of the ice cores and the gas records that are extracted from it. It helped to understand better the connection and the synchronization between Greenland and Antarctica, and north-south, and by this to understand the climate system in general, the ocean circulations, the temperature changes in the south and in the north. And all this information is important to understand also the present climate, of course.
Are we in time to prevent the worst scenarios of climate change? And if so, what measures do you think must be implemented to confront this global challenge?
This is a very difficult question. To answer this, I should know the behavior of the humans in the next 100 years, and this is very difficult to judge. Presently, it seems that we are not able to reach the goals we have set, because probably humans are not suffering enough yet. So I think to solve the problem is we have to improve efficiency. We can learn a lot from nature. Nature is very efficient in using resources and recycling and in the use of energy. So I think efficiency is the most important that we should improve.
Could you explain the model you developed to understand climate change through ice core research, and what have been the fundamental contributions to this field of research?
We have developed a range of climate models, ranging from very simple conceptual models to models of intermediate complexity. All these models are suitable to understand climate change on a very long time scale of several ice ages. This is suitable to interpret and understand the ice core record of the last 800,000 years.
What fundamental lessons can be derived from your research about the current state of climate change provoked by human activity and its potential future impacts?
Well, we have three lessons learned from this research. First of all, carbon dioxide concentrations today are 35% higher than ever in the past 800,000 years. Second, warming is unprecedented in at least the last 2,000 years. And third, we have learned from polar ice cores that there are instabilities in the climate system, abrupt changes that could actually happen in the future due to the large perturbations that man is inflicting on climate.
Are we in time to prevent the worst scenarios of climate change? And if so, what measures do you think must be implemented to confront these global challenges?
Looking back on climate change, our ancestors and pioneers already 40 years ago have alerted to the problem of anthropogenic climate change. Time is urgent now to act, and the act must be the reduction of greenhouse gas emissions as urgently as possible in order to keep within the temperature bounds that are given by the Paris Agreement from 2015, which means keeping global mean warming well below 2 degrees Celsius.